Yep. And then I need to share my screen. I have way too many tabs open. I'll just do entire screen. And then, can someone just unmute themselves and tell me that they see the paper?
Yep.
Yeah, see it well.
Okay,
Yep.
cool. Great. Thank you very much. Hey, everyone. Welcome to NPLAN's Paper Club. Today, I'll be presenting Flamingo, a visual language model for few-shot learning. So I think this paper brings together a lot of very interesting ideas. I also like that there's a flamingo in the title, right over here. But what's I think there's two main ideas that are being brought together here. And the first one is this idea of general visual language understanding. So if we go to the introduction, they say over here, one of the, well, actually, where do they introduce general visual language understanding? I guess I'll just introduce it because they don't say it. But and that's the idea that we can create models that have a generalizable understanding of how images and text can be combined in a semantically good way. Good is probably not the best way of saying it, but like, for example, a model that understands when you say you show a picture of a giraffe and then you start saying the animal in the in the image has a long neck and spots, and that the model can understand that it's a giraffe, you know, being able to combine the two. So that's kind of the goal of this paper, which is to create like a very large generalizable visual language model that can generalize to new tasks. But it's not only that, it's also the idea that the model can generalize with few shots, which means that very few data points. For example, when they're evaluating their model, they evaluate it on a new task, a task that it wasn't trained on, and they're evaluating it to with using just 32 data points at most. In some cases, it's like 2 to 4 data points. So what this paper is doing is trying to create a generalizable visual language model that can generalize to a new task with very little data. So I would say it's a pretty a daunting task, but at the same time, they take a lot of ideas from language models, large language models, which have shown to be able to do exactly this in order to inspire their method. Let's see, is there anything else that I wanted to talk about before we start going through the paper? I'm just going to go to the introduction. Yeah, I guess, and just because I think it's a good motivator, as they say, in their introduction, one key aspect of intelligence is the ability to quickly learn to perform a new task given a short instruction. So kind of the motivation for this paper is that we are looking to make intelligent models, and this is a key element of that. Just like, I think the example I've heard a million times is that you show like a child a cat and you say this is a cat, and then the next time they see a cat, they know that it's a cat. And that's an example of one-shot learning because you just had to be instructed that that's a cat, and then you know. So yeah, this is the type of inference that they would like our models to be like our models to be able to do as well. Okay, let's just quickly go through everything. I'm just going to go through everything as it's presented because I use the highlights that I've made to like remember what I want to talk about. We've talked about that. We've talked about that. I mean, another thing we'll go through later is that I think one of the main contributions of this paper is actually the data sets that they use to train the model, because they've actually created these massive data sets, massive multimodal data set of vision and text text, and actually it's also video, images and text, and then video and text. And that's one of the key reasons why they can do so well, in my opinion. Okay, and then they're just in the introduction, they're talking about the results, but we'll go through the results later. Maybe we can look at some examples really quickly in this massive figure, so you can see what they consider to be like few-shot visual language understanding. So here's an example of where you have like an image, and then it says this is in chinchilla. They are mainly found in Chile, and then an image, and then it says this is Shiba. They're very popular in Japan. Oh, this is a Shiba, sorry. And then they show a flamingo, and they say this is a flamingo. They're found in the Caribbean and South America. So here, the model has maybe never seen some kind of description like this before, but maybe it has because it's being trained on such massive data sets. But the idea is you give it like an image and then some kind of style, some kind of like structured response, and you want it to give you the same response for a new image. So this is how it's few shot. You get like you're actually feeding in as an input to the model what you're looking for, but then you want it to generalize to a new example. Yeah, sorry for the coughing, by the way. Like I said before, I have a residual cough from the flu. But in their introduction, they actually introduce like what's the current paradigm in this problem setting, or for this problem, which is there's the best results that they're getting right now for this type of having like a generalizable model that generalizes to new tasks. So you pre-train it and then you have very little data for the new task, is with fine tuning. So you're taking like the last layer of your model, or maybe the last couple layers or something like that, and you're training it for a much shorter amount of time on a smaller amount of data. And that's what's the current state of the art right now. But they point out that for this state of the art, of fine tuning, that the downsides are that there's per task hyperparameter tuning, and it's also resource intensive. So for example, as they show later, the models need a lot more data points to get good performance than Flamingo does. And also just that you're kind of like having to do a hyperparameter search for each task, which in itself is like you might be overfitting to the task. I don't know. So they talk about this as the current state of the art, but they do also point out another method, which I don't think we're going to go to in detail because they don't really compare to it. But there is a model, or I guess a couple models, that do vision language training, and they do it in fact, and they generalize with zero shot adaptation. They're trained with a contrastive objective. Basically, the model that the model is trained, and you can see here it says what it kind of does. But the model is trained so it gets an image, which is an image and then a text, and it has to say how similar they are. Like, are they describing the same thing? Is this the same information portrayed in two different ways? And so the output of the model is a similarity score. And what they're saying is, so for what we're doing, the current state of the art is fine tuning, which needs a lot more resources, but there is this other model which needs very little resources. In fact, it's a zero-shot adaptation model, which works really well, but it only works well for classification, like saying, is this image related to this text, and things along those lines. And so the contribution of this model is that it does language generation. So instead of just saying like these two things are similar, you can literally output a new answer for a sequence of images and text. We'll go over, this is just the experiments. And so the first thing that they talk about in terms of inspiration is that large language models are good few-shot learners. So they're trying to take inspiration from that and trying to create like a large visual language model. Makes sense. And that the model that they're suggesting is a visually conditioned autoregressive text generation model. That just means that you're generating based on all of the past information that you have in order to generate. And so, for example, yeah, we'll go with that. So that's good enough for now. So the contribution, besides the idea, is that they come up with some novel architecture components to stitch everything together, which I actually thought was quite interesting. And they talk about how Flamingo, like as a model, can do things like take high resolution images and videos because of the architecture they've chosen, which I guess is maybe not novel, but I don't think we're at the point yet where we're like really there with doing like high resolution image processing in videos with deep learning models. Okay. Okay. Well, we'll go back into the architecture later. They talk about contributions. We'll go into the architecture, the results later. Is there anything I want to point out? Nope. Okay. So yeah, they talk about the key. Okay. So I guess we'll talk about the architecture. I try to, I hope I present things in like a, from simple to complex, but so in terms of the architecture, the fundamental idea of it is this thing here, which is the what we're calling autoregressive, which is that when you're trying to infer like y is text and x is images and y is tokens. So like y itself is a sequence of tokens, where a token is like a word or some set of characters that might be sub-word level. And so basically what it's saying is the way that this model works is that it takes everything from before that token that you're trying to generate and looks at it, which is like all the tokens that are text and then all the images in the sequence that it sees before. I actually think this is a more important distinction at training time than test time, because at test time, you're never going to have the later tokens to look at in a way that you could pay attention to them. But at training time, you probably will show the entire sequence, and then you just use masking when you're doing when you're attending to the sequence in order to make sure that you're doing it in an autoregressive manner. Cool. So the way that the architecture works is, by the way, one thing I really like about this paper is I think a lot of the figures are quite good. Like they're pretty easy to understand, good colors. Anyway, one of the key ideas.
The vision encoder,
Mm-hmm.
are they big models or are they small?
Yeah, let's actually jump to the to the text here. So there are vision encoders, pre-trained and frozen normalizer, free ResNet. We use the F6 model. To be honest, I don't know how many parameters are in the vision encoder, but I do know that the language model that they're using has 70 billion, like in the large Flamingo model, has 70 billion parameters. And so, and the Flamingo model has 80 billion parameters. So if that's true, at most the vision model could have would have 10 billion parameters, but I think the additional architecture, like the additional layers that they stitch into the models, also have a lot of parameters. So it's like somewhere between 1 and 5 maybe billion parameters, if any. Long story short, I don't know, but it's nothing. It's not as many. It's an order of magnitude less than the language model they're using.
Mm-hmm. And the language model is also pre-trained, right?
Yeah, both. So if you look at this figure, you can see that they have their vision encoder, which is when you see this, if you can see my cursor, there's like a dark blue with a snowflake on it, which means pre-trained and frozen. So their vision encoders are pre-trained and frozen. And so what they're doing is, so they take an image, they put it through the vision encoder, which is it sounds like a ResNet model, but maybe I think there's more to it. And then they have this perceiver resampler, which based on my understanding, and we'll go through this later, is actually, it's literally just sampling, because the output of the vision encoder is a sequence, and it might be 2D, but I think it's 1D. Let's see what it says over here.
1D, yeah.
It says, we use the final output stage, a 2D spatial grid of features that is flattened to 1D. Yeah, so they make it 1D. And then the perceiver sampler, it says it takes as input a variable number of image or video features from the vision encoder and produces a fixed number of visual outputs. So it's literally just sampling like which elements in the sequence to take randomly. It's yeah.
So this a big model in itself. It makes use of big models, but it probably adds about similar number of parameters to it on top of that, or
I don't. So for example, the perceiver resampler, this is just a sampling layer in the sense that it has no parameters. The
gated attention, that is the thing that sort of is the meat of the Flamingo, right?
Yeah. And we'll go over here to look at it, but so one thing that here's the text, by the way, and what you can see is like they encode images and they
sorry, there's a question. What do you mean by frozen in the chat?
Oh yeah, so thanks for the question. What I mean by frozen is, so you have a pre-trained vision encoder and a pre-trained language model, and so they've already been trained. They have some weights, and frozen means that when you're back propagating through them to train your network, you are back propagating through these layers and these models, but you're not updating the gradients. So they're frozen because no matter what you do, the weights of those models and those layers aren't going to change. And so what you can see over here is that you get these images, but they're actually not within the text sequence. Instead, you have like an image token that's put in the text sequence. And then you are fed separately the images. So if you look at, this is what I'm highlighting here, this is the original interleaved text and images. And what they do, they take the images out, they encode them, they sample from them. And then they also take the text where they're just indicating the position of the image in the sequence with the token, and they're feeding that into these layers. And the way that this model works is they take the language model and they have a gated cross attention, which will go in layer before every language model layer. So if you had like 10 language model layers, you'd add 10 gated cross attention dense layers before it. And I actually found this very interesting because essentially these, I always thought of layers as working on top of each other. And so I was thinking that by stitching in an extra layer in between all of them, it's like, and freezing the language model layers, that you're kind of like changing the progression of the pre-trained progression of information through the language model. And I just was like, it's very surprising to me, because if anything, usually I've heard what you see here as how you use a pre-trained model, which is that you, like for example, with ImageNet, the classic pre-training example is that you take ImageNet until the last layer, and you either, if you're using it on a new task, you fine tune the last layer if it makes sense, or you just take everything up to the last layer and view it as an encoder and train a model like something on top of that. But here they're literally stitching layers into the language models so that they're one after another.
Yeah, it might be more of a filtering, right? This gated attention, that it's not really changing bits around so much more than setting sum to 0 so that they might be just filtered. I think it's also quite important that the images are being constantly input again into the model, right? On each layer, that it's not like one continuous block where the information sort of trickles down, but rather you sort of process the information, but at the same time you have the option to look at the original picture again and almost like I think when we think through something, right? We think, but then we start looking at it from the beginning again, and so on and so forth.
That makes sense. And so let's take a look at this gated cross-attention layer. So as we've said before, you have, so each new language model layer is this gated cross-attention layer, and then the language model layer. And the gated cross-attention takes in X and then Y, where Y is the text and X is the representation of the images. And I'm actually going to skip this middle image and go straight to here. So this is a great gated, this is like some pseudocode for the gated cross-attention layer. And you have Y, your image sequence, your text sequence, X, your image sequence. And then these are actually learnable parameters of the layer, which are used to gate the layer. And what do they mean by that? So if you look at these second two lines, they're just a language model. So I think we can ignore them. It's really, this is the crux of the addition. So what they're saying here is, okay, like the image sequence representation, so you have a sequence of token embeddings is equal to the original sequence, and then plus 10h of your gating parameters. So what that's doing is 10h is it's limiting the I guess it's being used as like a way of maybe not letting some through or letting some through. And then you have your attention, which is what your query sequence is your image sequence, your text sequence, and your like key sequence or your value sequence is your image sequence. So it's saying like paying attention for each token in your text sequence, how much should I pay attention to the image encoding I have? And then we gate it, I think for stability reasons. And then they basically have a second layer which is a feed forward layer with gating as well. I think there's a good explanation of why they have this gating thing here. The one, I think, important part of this, which we'll probably go over later, like as a reason why they have this in here, this 10h, is because they set the parameters of both of these attention layers to, of these gating parameters to 0, which means when they start training, this whole term is 0, and this whole term is 0. And what that means is that when they start training, they're actually only using the language model to do generation or to train the model. And it's only after like the first gradient update, as long as the gradient update changes the weights of these parameters, that you actually start taking into account the images as well. And they say if we take away this component of the layer, this gating component, then they hit stability issues. And so that might be the reason why they have the gating component in there, just to maintain the stability of training. So yeah, that's one of the reasons why it's there. And by the way, if anyone's wondering why it's called cross attention, it's because you're not attending to the same thing that you're querying. So like you're querying text, but the values that you're looking at are images. So like image embedding. So that's why it's called cross attention. Usually, like in transformers, we see self attention, which means that you're attending to the same sequence that you're querying. If anyone's wondering. So yeah, that's how the language model, or this is probably one of the main method contributions of this paper, which is this gated cross attention, and it's how they're stitching together multimodal inputs. I think an interesting part of it is I could totally see the same thing working for other modalities. So for example, maybe you have a really good, which we do have, like maybe we have state-of-the-art models for point clouds, state-of-the-art models for like sound sequences. You know, there's all these different models that are for different modalities, and this could be a way to stitch it together with text such that you can generate text off of that. So yeah, I think that's pretty interesting because it means that maybe some follow-up work will be like just trying all of the state-of-the-art encoding models for different modalities of structured data. Cool. We talked a lot about how they're interleaving the gated cross-attention layers with the frozen language model layers. I don't think there's anything that needs to be mentioned there. Nope. And then, Arvid, are there any questions? Just because I can't see it while I'm on this one. If not, I'm just let me know if there are, if you could, and I'll continue otherwise. So, okay. Okay, so we talked a little bit about the architecture. A key component of this architecture, I just pick out details usually that I think are important for understanding, is that the model only directly looks at the previous image when it's performing cross attention. So, for example, when we were looking back here, when we were looking back here, this X is just the previous image. So if we look at this example here, then the text, "This is a very cute dog," would only look at this image of the dog, and then this is, and for the cat is, would only look at the cat. But they point out that even though that's true of the way that this attention is being performed, that by having multiple layers on top of each other, you do start to get, you will get information from the previous images. So this is, for the cat, we'll also see the dog after the first images, after the first layer, because, or information from that image of the dog will be passed on because of the attention that's being performed over the whole text sequence. I hope that makes sense. And then
Mahed has a comment.
What?
I think Mahed has a comment or raised hand.
Okay.
Hey, Peter, can you hear
Yeah.
me?
Yeah.
So, is it correct to say that how well this model performs is it largely dependent on how well those pre-trained language models have essentially been trained? Because from my understanding is initially you don't have any so the because of those gate attentions, sorry, those gates, largely the pre-trained the information from the pre-trained models is used to generate the output. So it might be like they're trying to mimic the fact that when a kid tries to understand, it has a supervisor saying, okay, that which has much better large priors, okay, that's a picture of a cat, and then the next you've established this prior information, now it's your turn to condition your model. Is that why it's how it's working?
Yeah, so I would tend to agree from the perspective that probably just like randomly initialized networks, like if you just randomly initialize the language model network or the vision perceiver, the visual encoder network, probably, I mean, yeah, it shouldn't work so well. But I think the reason I'm sure it's very dependent on it, because they wouldn't be using these large pre-trained models otherwise. I think the idea for me is that these pre-trained models learn features and like even high level features because they have stacked layers. And really you want to use those features because they're very useful generalizable learned features because they've been trained on a massive corpus beforehand. And so if you didn't have those learned generalizable features that you have from these, like the vision encoder and the language model, probably it wouldn't work as well. a corollary to that is in their experiments, they do a, where is it? Yeah, I guess it's, unfortunately, it's broken into two. They look at the importance of the training data mixture. Actually, let's introduce the training data first. So you as I had pointed out, you start out with these pre-trained visual model, a visual encoder, and then a pre-trained language model. But then you do train them on so you train those cross-attention layers on a very large corpus of data. They have 3 data sets that they train it on. I think it's 3, yeah. The first one is this multimodal massive web data set, which I wish I could, I'm going to just go back to this real quick. All right. Sorry, guys. Cool. So the first data set that they use is that they scrape the web. They look at the HTML in websites. I don't know how they choose the websites. Maybe it's completely random. And they looked at 43 million web pages, and they just get the text and the image, and they use images relative to the text base. On the they're saying they find the position in the sequence of the text, of the images, using document object model, which I don't know what that is, but I'm sure a simple Google search will tell you. So their first data set is something they scraped from the web. Their second data set is, which I think they scraped it from the web. Okay. The second data set they use is this align data set, which is images paired with alt text. So it's 4 data sets, sorry. The third one is, they call it long text and image pairs, because I guess the previous data set only had like one sequence or small sequences, is where they collected 312 million image and text pairs. And then the second one is video and text pairs, where they collect 27 million short videos with paired sentence descriptions. And I'm just going through this because that is so much data. That's why I think one of the massive contributions of this paper is they've created, so they have 43 million web pages of sequences of text and images that they've collected. Then they have 312 million text and image pairs, and then they have 27 million short videos. And this is something they did. I don't know how they did it. Maybe they used Amazon Turk, but that's a lot of data. And I bet that that's like a very important reason why this model works so well, because they were able to create this data set that wasn't there before. Yeah, I think that's also a massive contribution, because hopefully other people can get access to these data sets now, which means that we have for vision and language, like vision and language, combined vision and language understanding, all of a sudden we have like this massive new set of data that we can work with. So anyway, I think that's cool, and I think it's a major contribution. And they point out that in their experiments that including or not including different data sets that from the ones that they have has a massive impact on performance. They have like an overall score that they use for saying how good performance is. I didn't look too much into it, but let's assume they have some way of saying like this performs 80, this has a score of 80, this has 70. So that website data that they collected, if you take it out, the performance decreases by 17%. And then if you take out, let's see, what's the next one? Removing the conventional paired images, so the ones from the aligned data set, and the other one that they created decreases it by 9%. And then also, if you take out the video data, it decreases the performance on video, the video tasks that they're generalizing to. Okay. So yeah, the data that they have definitely has an impact on performance. It'd be interesting to see, because the only data that they had before all the stuff they collected was this aligned data set. if they had just trained a model on the aligned data set, whether how well it would have performed. But maybe that's in the appendix. I didn't get there.
It's
So
probably also like,
mhm.
did you know when how you mentioned that they had to scrape a lot of data, and they also mentioned somewhere, I think it was in, oh, it's in the same page you're on, where they mentioned that each of the data set is weighted by a scalar lambda, and then they did say that it's very important to choose this correctly. I'm presuming it's because majority of the data they might scrape might not be useful. For example, they do say they go through these memes, which is not useful because, as you know, the image, the text will not describe the image correctly in memes. They're designed to be more funny, like um, the captions might be more like, here's a picture of Will Smith, I don't know, slapping somebody. That doesn't really explain the image, so the contextual information might not be relevant for the model. So it would be great to know how they decide lambda m in that case.
Yeah, I agree. So the way that they actually did, so a first component of the way that they're training, that's an important, what they consider to be an important part of their method, is they say we accumulate gradients over all data sets, which we found outperformed a round robin approach, which means that they mix data sets. Actually, it doesn't even look like they. Yeah, they must have just mixed. They mixed data sets when they were training instead of training on each data set separately. But they weighted each data set, as Mahad said, differently. The way they did that is they had 17 few-shot text generation tasks that they evaluated the model on. And they chose 6 of those, and they used those as a validation set to choose that hyperparameter and other hyperparameters that they were using. So they tailored it based on performing well on those tasks, on the validation set of those tasks. But then one of their big points is that they tried on 11 other tasks where they didn't do any validation on those, and they still get really good results.
Yeah.
Okay. And so this is how they're training their models. They're maximizing the negative log likelihood of the text that they need to generate. So they have these sequences of text, generating the text, and they mix data sets when they're doing their gradient updates. So they accumulate gradients over all data sets instead of going on one and then the next and the next. Task adaptation with few shot. Okay. So they just point out at the end of their method that we perform open-ended evaluation using beam search for decoding, which means that they're using beam search to generate text. And I guess open-ended evaluation means when there's not like and anyone can tell me I'm wrong or if they have another idea, is like they're just generating text, but there's no like right answer, like an exact right answer. And then close-ended evaluation, they're using the model's log likelihood to score each possible answer, which, yeah, makes sense. Okay, experiments. We've talked about this. They evaluate on 17 different tasks and only use 6 to do hyperparameter searching. So they say the other 11 are ones that we can like say that show how well it generalizes, their model generalizes. Is there anything I need to say? No, there's not. And so they say they have like 2 contributions in terms of few-shot learning. One is that Flamingo is often competitive with state-of-the-art methods, additionally fine-tuned on up to hundreds of thousands of annotated examples. So it beats fine-tuning even sometimes. And yeah, we can actually, let's see if we need to look at the results for that. Okay. Yeah, we'll look at the results because I think that's more instructive than me just going through the text. So here's their mega table of results, and they have 3 different models. Their small 3 billion parameter model, then the 9 billion parameter model, and then Flamingo, which has the language model Chinchilla, which is has 70 billion parameters. They give you the state of the art for zero or few shot learning, and then they have the state of the art for pre-trained learning, which is, or like fine tuning, sorry. And the reason why it's in gray is because they have to use a lot more data than here. So here they're using, this is 0 shot, then there's 4 shot, and then 32 shot learning. But for fine tuning, they use all the data for fine tuning except for like a held out test set. And as you can see, the model outperforms all the other models, like all of the state of the art for all of the tasks. One thing that I think is interesting is that the smaller model outperforms on one of the tasks, but I guess it's by such a small margin. I don't know if you could argue that. And then even though if you look at them in gray, so higher is better, by the way, if anyone was wondering. If you look at the numbers in gray, you can see that, yeah, for a lot of them, like in this, for example, in this case, the Flamingo outperforms the pre-trained and fine-tuned model. Over here, though, it doesn't. It's less. And for most of them, it's less. But anyway, so this is like the main table of results showing that they're state of the art for visual language understanding on all of the tasks, and then that they beat some fine-tuned models. Maybe that shows that the fine-tuning overfits in a lot of these cases, and that's why they do better. Yeah, so that's the main table of results. Then they go over a couple of other things. Okay, cool. Scaling with respect to, okay, so they show that their model performs better as you increase the number of parameters and the number of shots. One interesting thing about it is that they only train their model on sequences of up to 5 images, but they evaluate their model on up to 32. I think that's a really cool result because it means that the model performs better, which means that it's actually taking into account more of that information each time, so more of the images. So even though it only ever sees 5 images, it's most likely taking into account information from all of the 32 images at test time in order to perform its inference. And then they also show that with fine tuning, they can perform better as well. Let's see if they have a fine tuning. Yeah. Here's the fine-tuned results for their model. So for Flamingo, they also achieve state-of-the-art results over fine-tuned models over the current fine-tuning results. Yeah, so you can also fine-tune it and get great results. We talked about the data set. Visual conditioning on the frozen language model. So they did some ablation studies as well, and we were kind of talking about this before. They say we use the 0 initialized 10 gating when merging the cross-attentional errors to the frozen language model output. Without it, we see a 4.2 drop in overall score. And that means the 0 initialized gating. So I guess if they randomly initialize the gating, because they say moreover, we've noticed that disabling it, which means taking it out, leads to training instabilities. They also talk about catastrophic. I'm forgetting somewhere. Okay. So the gating is important. They see that it has an improvement. One thing that I thought was interesting, and it's a question for anyone else who's maybe had some time to think about this, is that like some of the data, including some of the data or not, has a pretty big delta in performance. But some of the other times, the delta in performance is really small that they're talking about. That, like, for example, this 0 initialized 10 gating is important because it leads to a 4.2 drop in overall score, 4.2%. And personally, in my work, sometimes you can get that kind of drop even by just having different initializations of the weights. So I wonder if if it's meaningful. But I think the fact that they put it in here means it is. Like maybe their performance when they dip based on how they initialize weights is very much like they see the same performance each time. It's not as variable as the stuff that I've done in my work. They talk about how over here, they talk about how these gated cross-attention layers, they actually add a lot of parameters to the network. And they found that by just putting one every fourth block instead of every language model block, it accelerates training by 66% while decreasing overall score by 1.9%. And for that reason, for Flamingo with 9 billion layers, they put a gated cross-attention layer every fourth layer, and then for their big model, which they call Flamingo, it's every seventh. So they don't even put these every layer, but they put it every seventh layer. They did an ablation study to show which of their that they used the best encoder, like in the sense that they saw a better performance than other vision encoders. And lastly, here's the part. They looked at the importance of freezing the language model. So we verified the importance of freezing the language model at training in row. If we train from scratch, which means that we, let's see, if we train from scratch, does that mean that you're just, I think that doesn't mean that you are initializing a new language model. I think it just means that you're not, all the layers aren't frozen. We see a decrease in performance of minus 12.9%. And interestingly, fine-tuning our pre-trained model also leads to a drop of minus 8%. So any type of unfrozen language model training performs worse, and they they say this is an indication of catastrophic forgetting. This is actually to me, this is actually a really powerful result because it's very useful in the sense that you don't have to train so much of your model. Means that you can take a lot of stuff off the shelf and use it to get state-of-the-art results, which is both interesting and like useful from an engineering perspective and many perspectives. Then they go into related work. I'm not going to go into that. We've kind of talked about it. And then discussion. Okay, I like their limitations page because they talk about they give an honest appraisal of their work and what could be some of the downsides. Or to me, it seems honest. I don't have a huge background, or I don't have a background in this field to know for sure. But they say, since first, our models build on pre-trained language model and a side effect directly inherit their weaknesses. So they say language model priors are generally helpful, but may play a role in occasional hallucinations and ungrounded answers. And then also language models tend to generalize poorly to longer sequences than the training ones. I thought that one was interesting because it seemed like their model performed better, but maybe that was just in terms of the number of images incorporated, not the size of the sequences. And they have poor sample efficiency during training, but I think that's more of the fact that they're so large. The classification performance of Flamingo lags behind state-of-the-art, but the models that are state-of-the-art, like the state-of-the-art contrastive models, they're trained exactly to do that. So I could see that makes sense. And then, yeah, let's see. Okay, so it says, so for the, they finally named the type of few-shot learning that they're doing, and they're calling it in-context learning, which means that they're not using gradients to update the model, but they're taking data points from the new task and they're inputting them into the model, as well as the example that you want to perform inference on, which is this in-context learning. And it says in-context learning is known to be highly sensitive to various aspects of the demonstrations, which makes a lot of sense to me. So that means that like maybe if you have flaws in it, when they say demonstrations, they mean like these two, if you see my cursor, these two pieces here. So maybe if you saw the chinchilla and it said, this is the Empire State Building, New York has great hot dogs. And then the second one said, this is a Shiba, they are very popular in Japan, then this would be completely wrong because the examples that it's using, one of the examples provides noise for like the answer that they're looking for. So yeah. sensitive to demonstrations, and its inference costs and absolute performance scale poorly with the number of shots beyond their low data regime. So again, makes sense. When you start, if you wanted to take into account 1,000 data points for this in context learning, it'd be very slow, and also probably there would be enough noise that it would be hard for it to give like a great answer. So the societal impacts, and this is the last thing I'll say because I wanted to open up the floor and ask some questions. It says one of the potential impacts is to enable non-expert users to obtain good performance in data-starved regimes, lowering the barriers to both beneficial and malicious applications. Which is, yeah, that sounds like it makes sense and sounds good. Yeah. So there was well, first I'll open up open it up to anyone who has some questions, but if not, there were some questions I wanted to ask and see what people's opinions are. So where should I go? I'll go here because it's a nice image. I'm just gonna go check if there's. Okay. So the two questions I had, one is about these. So a large language model is a model that's trained on data, on sequence data essentially, and sequence data where each element in the sequence is a categorical variable. That's what language is in terms of the structure that's provided to it for the model. And in terms of language, we've done great. And then now we have the same thing with these visual language models. They seem to be performing very well. I'm sure we also have the same thing for language models. And actually, we've had that for a long time with like pre-trained ImageNet. But my question is, does this, because these results are so amazing, does this approach, do you think this approach can be generalized to other forms of structured data? So for example, at NPlan, we work a lot with graph structured data. And that means that like most of our data can be seen as a graph instead of, for example, an image. But I was thinking to myself, at least, and maybe this is a bias which is unfounded, that there's so many different types of like data that's described in graphs. So for example, you could describe the hierarchy within an organization as a graph, but you could also describe like the way that birds interact while they're flying with each other as a graph, or you could describe the economy as a graph. So I was wondering if the data of graph structured data, it's harder to basically scrape enough of it or like it's not similar enough that you could do this type of scraping and come up with something generalizable. So anyway, my first question to everyone is just, do you think that we can do this with other types of structured data? Like, could we do it with tabular data?
Absolutely, you can. I think what I really like about this paper is that how they said that in early phases, in the previous study, you only had isolated single trained from scratch transformers, and the issue with what they wanted to highlight is that the standard convolutional networks, they have very good inductive reasoning, they have great inductive biases, and the language models are able to generate language semantics very good. And they wanted to bring these two ideas together and make a joint model, essentially, which has a pre-trained component and a component that is trained from scratch. So I think you can easily apply this to graph as well. I think the key idea, takeaway message from this paper is that in practitioners, most deep learning practitioners just go about training all their networks from scratch. But how this approach shows us is if you have a very good prior and you can filter information between your learning layers and your frozen layers, you can train the model on new data set very easily. And I think it can be applied to domains apart from vision and language, in my opinion.
Isn't there like a fundamental like information size you sort of give in when you pass on a picture, right? Whereas a graph could be potentially larger, whereas here the token size might be limited. On the other hand, because I think your encoders, when they turn your picture into tokens, right? So they already do some sort of semantic analysis of the images. So why couldn't a graph be an image that could be described in some general terms and then passed in a similar way? I don't know, which might be worth a try.
Yeah, that's a good point. Yeah, one thing I didn't actually, I'm sure it's in the appendix, is like whether the vision encoder that they're using can parse images of different sizes, or if they're all pre-processed to be the same size. Because if that's true, then you could also, because you can even represent a graph as like an adjacency matrix, and then use its like node features as, I mean, you can represent it as basically like two matrices, which if you don't care about the size of those matrices, you can do a lot with that.
Raised hand.
What?
Oh,
There's a raised hand by Sagar.
Oh, yeah. Thanks.
Yeah. Hi. Yeah, just wanted to comment on the question which Peter raised. So my understanding of the language models perform like generating coherent text as they do right now is because there is an inherent structure in language, like the rules of the grammar, which, although the tokens are categorical variables, still there are some finite slots where those variables fit, and this is what the large language models exploit. Um, as I said, the rules of the grammar. For graphs, I think that might be trickier because graphs are in themselves not any entity. They're like representation of something else. And I think if we go into domain specific graphs, it might be still true. Maybe graphs which represent a domain which has some rules, like how the nodes would be connected, and how many nodes will be connected to a node, and like rules of grammar, we could still apply these the same principles and have some similar results. I guess, like, if we represent text as a graph, like dependency graphs, I think this still works the same way. And maybe even language models internally, they have a representation. They do have dependency relationships. They do consider that, I think, in the multi-headed attention, somewhere in those deeper layers. So yeah, maybe the question boils down to the domain of the graph. I feel so, yeah.
Cool. Yeah, that makes sense. I'm just gonna cut us off just because we have we've gone a bit over time, but thanks everyone for attending, and I'm just gonna stop recording.